This is our second lecture. Hopefully you guys are all here to learn calculus. If not, you might want to leave. Couple things that we need to talk about with respect to the class. So again, all course material is on Canvas. So if you're not sure how to sort of navigate Canvas, if you can't log on, you need to let me know immediately. And once you log on, you need to just move around. It's not hard to learn. Everything's pretty self-explanatory. Just a couple things that you guys, should see there right now. A link to the lecture, the recordings. You should see that as soon as you log on. You should see whiteboards from they're going to be under what are called the modules. So again, all these whiteboards that I write on, you'll find I'll save them and I'll post them to the internet if you want to go back and read them. Homeworks are clearly under the assignments. And then check out the syllabus page. Has all that stuff. Has the syllabus, link stuff, or the Zoom info. And what a few of you have emailed me about and just asked me about, the My Math Lab stuff. So once again, let me reiterate, when you read the syllabus, I talk about there's this extra credit that you can earn, and it comes from what's called My Math Lab. So the publisher of our textbook, Pearson, has digital resources. So if you buy a copy of the textbook new, or you want to just buy the access code, you get access to all these digital resources. I post problems on there. If you do those problems, and you do so many of them correctly, you get extra credit points. So what I would encourage you to do is I would encourage that you check that out. And if you have the, if you want to spend the money on it, or maybe you've already bought that access or the book, then you can do it. It's not required, but it's there if you want. Now, as far as registering, it's pretty easy. So what I'll do is let me share this for you real quick. You should be seeing a Canvas page now. And when you go to, when you log into the class, what you'll see is something similar to this, not exactly the same, but similar. You'll see the link to the lectures, and then if you click on the syllabus page, what you'll see is you'll see links for the instructions. And if you hit this My Math Lab instruction, what'll pop up is a PDF. Are you guys seeing the PDF, hopefully? If you're not, let me know. And it's pretty self-explanatory. It gives you the code. You'll see the code for our course is this O'Grady business right here. And there's actually a link that you can click that will take you right there to register. So it's pretty self-explanatory. I encourage you, if you have the money to do it, but I'm not going to force you to. Does anybody have any questions about this? About the My Math Lab at all? Going once? All right. All right, if you have questions, all you have to do is ask. It's pretty easy to navigate as well. Okay. Does anybody have any questions about syllabus, book, anything that you may be unclear from what we talked about on Tuesday? Don't forget, if you don't want to speak up, I understand. That's fine. You can just chat. There's a chat button on here. All right. Well, if you guys don't have any questions, I'm hoping you guys took a look at the homework that's posted. Ideally, you guys can submit it tomorrow by midnight. Does anybody have any questions about the homework problems? Anybody?
I mean, I have lots of.
Oh, yeah, that's what we're going to ask about. So feel free to ask. I'd like to talk about them before we do anything else. So if you guys have a particular question, feel free to ask. I can start at the beginning, or if there's something specific you want to talk about, just let me know.
Yeah, I mean, if you have time, can you start at the beginning and just
Absolutely.
touch on a little bit? It's been like 10 years since I've done one.
Yeah, no, that's understandable. Yeah, so typically, so let's sort of transition to it this way. Typically, the way I shouldn't say the way, but a lot of times what happens when people teach a course like this is you spend a couple, maybe like a week or two refreshing all these ideas from past classes, algebra 1, algebra 2, trigonometry, geometry ideas. I typically don't like to teach it that way, because even if you learned it today or next week, when you need it in 3 weeks, you'll have forgotten it again. So what I like to do is I like to make the first homework sort of like this crash course review, to remind you of things that you learned before, but like most natural humans, we forget them if we don't use them. So these are sort of like the ideas of past classes that we're going to need as the semester goes on. I don't know why it says it's due May 26th right here. That doesn't make any sense. Please disregard the due date on the actual sheet. The homework is due tomorrow at midnight. If you need next week, that's fine too. Okay, so what we need to do is we need to start like this. So we need to think like this. In order to do any calculus, we must be able to work with functions. It's absolutely imperative that we are comfortable working with functions. So that means, do you know what a function is? If I asked you to define a function, could you? Now, honestly, most students at this point in the class would not be able to do that. You're likely familiar with them. You know that there's letters and parentheses, but other than that, most of us at this point in our math lives are very much overwhelmed by functions. So it is my philosophy that the best way to sort of become unoverwhelmed is to just work with them, not to make definitions and not to overwhelm you with all that, but to actually do things that are maybe intuitive. So a function can mean many things. It has very general and abstract definitions, but for us in this class, a function is basically a rule that associates one number with another number. That's what a function is. And before we do anything, let's think about why we would want to associate with one number with another number. And if you think about it briefly, it's not going to take long for you to get it. I mean, just observe the world around you. Go to the grocery store, put gas in your car, go to the movies, go running, drink a glass of wine if you're 21. If anything that we observe in our world or things that happen to us, if we'd like to discuss them and analyze them, at the very basic, what they do is they come down to one quantity depending on another quantity. For example, you go to the gas station. The amount of money that you are charged to put gas in your car depends on one thing. What is it? It depends on how much gas you actually put in your car. There is a relationship. Your electric bill every month depends on how much electricity you consume at home. So we see that in the world around us, we have multiple quantities that depend on each other. And what we want to study in Calculus 1 is we want to study the most basic scenario. And that is where one quantity depends on another quantity. We have a relationship. This quantity is related somehow to this quantity. So the abstraction of this is what's called a function. Now, in the real world, we have multiple things that are dependent on other. Imagine a small business, a very small business. Imagine you're going to sell lemonade on the side of the road. Well, if you wanted to sort of quantify and analyze your profits and revenue, well, there's more than one or two dependencies there. There's lots of dependencies. So we're not even at that level right now. We're basically saying if we have two quantities that one quantity is dependent on the other, how do we study that? If you think back to Tuesday's class, I said that calculus is really the mathematics of change. And imagine we have two quantities. I have my left-hand quantity and my right-hand quantity, and they depend on each other. And really what I want to know is if this quantity changes, what happens to this quantity? If I sell a product and the number of products I sell increases, well, we might assume that my revenue increases, right? Or if one quantity is my debt and the other quantity is my payments on my debt, as I increase my payments, my debt decreases. So you can imagine that we have quantities of things that depend on each other, and we want to study what happens to one when the other changes. Look back to Tuesday's lecture. We had geometric relationships. We had a rectangle. Its area was related to its length and its width. The triangle's area, its size, is related to its base and its height. What happens to one of those quantities if the other changes? Okay, so I don't know if that makes any sense, but if I can get you to think about a function that way, is relating two quantities, then I think we have a better chance of doing this. So if you do that, we have the following. So we give two quantities a name. So let's think of it like this way. So we give two quantities names. Say, you guys are familiar with this, X and Y. And then the rule that relates them might be named, I don't know, let's say F. F for function. So it's just like anything else. We give names to everything. This is a phone. This is a pen. I know I have paper. We give names to things. So in math, what we're going to do is we're going to say we want to study how quantities that depend on each other change. So let's give quantity 1 a name. sometimes we call that X or maybe Y, and we give quantity to a name. Maybe we'll call that A or B or X or Y. So this is where the letters come in. We're using letters to represent numbers. And then what is the convention? Well, it's convention to write the rule. So what we'd like to do is express the rule symbolically. Like we might write it as y equals f of x, where f of x is some rule. What is our rule? Our rule is something like, I don't know, let's do a very basic one. How about x squared? So what does this relationship say? Well, this gives us a relationship of squaring. So we couldn't possibly write down what this relationship does to every number, because there's infinitely many numbers. So what we do is we come down with this symbolic description of the rule. So if you want to think about this in English, what this thing means is, by the way, for those of you who are unfamiliar, this thing reads, in English, this reads f of x. So what does it mean? Well, let's think about what it means. Well, we give names to these things. So you might remember this from your days in previous classes. So we call x the independent variable. And then we call f of x, which can be called y for short, we call this the dependent variable. So one of the most common errors is when you guys see this f with the parenthesis, x parenthesis, that represents a number. We just don't know what number it represents right now until we give it a specific input. So what do I mean by that? Give it specific input. Well, let's go to the next page and think about that. Does anybody have a question, by the way, about what we're saying here, or a comment? Feel free to chirp out. Do not be shy. Okay, so let's be very clear with this. So if x is a number, f parenthesis x, which reads f of x, is also a number. And what number is it? Well, it's what? It's given by the rule f. So right now this might seem a little overwhelming, but let's just go back to that function we talked about, on the previous page, this x squared idea. And by the way, there's some of you who are probably bored. Here's what happens in a class like this. Some of you are like, holy hell, this is so easy. Why are we doing this? And then some of you think that we're building rocket ships right now. So I can assure you this ain't rocket science. And I can assure you this is not super easy. There are going to be things in this class that some of you in the beginning especially will think and feel like you're bored. And there's going to be things in this class that the whole semester some of you feel completely overwhelmed. That's the nature of mathematics. some of this stuff is, overwhelming just to look at. So, you guys have to, sort of realize that there's a happy medium here. So let's look at this in an example sense. So let's look at this particular relationship that we said before. If I tell you that my function is, what this guy does is it takes a number and whenever you give it a number, it spits out a new number. This rule, and this rule is given by its squares, whatever you plug into it. So if I have this particular creature, then what happens if I do something like f of 3? Well, f of 3, what does this mean? This means I take 3 and I square it. And of course, we should all know that that's 9. If I take f of -2, I have to take -2 and square it. And when I do that, I get +4. So this is probably the most simple example I can give you of what we say. We are giving you examples of evaluating a function. We are computing values. So if I can be even more descriptive, I think it could be helpful. Let me get a different color so we see what's happening. If I come over here and write f of x equals x squared, another way of thinking about this is this right here is the input. And then this creature is what's called the output. Every function that we're going to deal with in this class, you can often think about as sort of some like box or some machine where you give it a number, the function takes your number and it does something to it, and then it's going to give you a new number. Now, it's possible that the number it spits out is the same number that you gave it. For example, if I go over here, I mean, it's quite possible that I can plug a number in and it spits out the same number I plug it in. If I plug in 1, it's going to spit out 1 squared, which is just 1. So in that sense, it's not a new number. Does anybody have a question about this example? Now, here's another thing to keep in perspective. Some of you probably have seen lots of functions in your math courses before you got here. Some of you may have been very limited in your exposure with functions. That just depends on where you went to school, how your teachers taught it, how many classes you took. Many of you are sitting in this class and maybe you only took 2 or 3 math classes in high school, where others maybe you took 4 or 5. So every one of you is going to have a different sort of level of experience with this stuff. Does anybody have a question about this? Again, as I said before, feel free to speak up. You don't have to be shy. So we'll call this example 1. And then we'll go to the next page and do another one. And we'll build up to what's on the homework. So let's do another type of relationship. Let's call this one G. I don't have to call them all F. I can call them anything I want. I'll call this guy G. So let's say that G is going to take its input, square it, then it's going to multiply it by 3 and then subtract 2 from it. So let's look at how this creature interacts with some different numbers. For example, if I plug in 0, it spits out 3 times 0 squared minus 2, which is 0 minus 2, which is -2. So some of you don't need all these steps, and that's fine, but some of you, it doesn't hurt to see them. What if I plug in 5. If I plug in 5, I get 3 times 25 minus 2, which is 73. So we'll go a little faster. All right, now one of the things that many of you hate, what if I plugged in like 1/3? Now I have 3 times a ninth minus 2, which is 1/3 minus 2. Which becomes negative 5/3. If we can do our arithmetic. Two things that are going to be sort of, and I'm not assuming this, but this is what history tells me. Most students at this level of math still struggle with negative numbers, and you still struggle with fractions. And you have to get over this sort of, I don't know, I don't want to call it a fear, because I don't think you guys are, well, some of you are afraid, you get overwhelmed. You know, you have to be able to work with rational expressions. That's the fancy word for fractions. And you have to be able to work with negative numbers. Does anybody have a question about this? Let's do one more, what I would call a very basic example. And I'm going to use different letter again for both things. I'm going to write, call this function n, and it'll be, the variable will be t, and let's write it as 1/t. So let's choose a different color here. Suppose we wanted to know what is n of 1. Well, n of 1 is just 1/1, which is 1. N of 7 is 1/7. Not much you can do there. N of 1/3 would be 1/1/3, which is just 3. Now here's another important concept. What if I try to plug 0 in here? If I try to plug 0 in here, that doesn't make any sense. There's no such math, there's no meaning to dividing by 0. There's no mathematical way of describing 1/0. So what we say is, we say this is undefined. So this particular function, which I called n, doesn't have any way it doesn't have a rule for how to handle 0. You can't give it 0. So when you can't plug a particular number in, what we say is, we say 0 is not in the domain of n. So you should be familiar, maybe you're not, you may have forgotten it. If it's been 10 years, I think Heather, you said it was 10 years for you. There's these words like domain and range that turn out to be very important in certain areas, and we need to be familiar with them and what they mean. Does anybody have a question about these first 3 examples? Anyone? Going once, going twice? I'll get a sip of water while you ponder it. Okay, so if you look at the homework then, problem 1 is just an example similar to these. It's just the expression is a little more involved. So let's do an example that's not identical to that, but similar. So this will be our, what is this, example 4. So for fun, we'll call it G, just like we did in the homework. And let's do something like 3x squared minus 5x plus 10 over x plus 2. So if we wanted to evaluate a few numbers, what would g of 0 be? G of 0 would be, if I can take some liberties here, anytime I multiply by 0, I get 0. So this thing simplifies to 10 halves, which is 5. So if you have a question about that, feel free to let me know. So again, some of you may be able to do something like this in your head, others may not. So every one of you is going to be at a different level. You have to understand that. And you also, you can't be shy to tell me that I'm moving too fast or I'm moving too slow. I don't know that unless you guys speak out. What if we plugged, say, -2 in here? This would be 3. Let's go real slow with this one. -2 squared minus 5 times -2 plus 10 all over -2 plus 2, which again is undefined. Why is it undefined? Because I have 0 in the denominator. Does anybody have a question about that? Now, what we might say here, and the correct way of saying this is the domain of G is all x not equal to -2. That's one way of expressing that. Does anybody have a question about this? Going once, going twice. You guys having fun yet? How many people are with us? There's only 6 of you. Can you believe that? Only 6 have joined the party, and we don't even know if half of you are even there. You could be playing video games or sleeping or hanging out. All right. Does anybody have a question? Last before we move on to the more what's more interesting. Okay, so here we go. So we can add, subtract, multiply, divide 2 functions to get a new one. This is something that you would have done in an algebra class. For instance, things that you might remember doing. Remember, like adding like terms and multiplying, and things like the distributive law. All these things that you learned years ago, you probably forgot, but it's kind of like riding a bike. They will come back to you. We use those all the time. One of the other ways that we can get a new function is we can, what we say, compose 2 functions. So this is what's called composition. So symbolically, what does this mean? So let's just write down what this means, and it's going to look overwhelming for some of you, and that's okay. But we want you to think about what this means. So take two functions. Let's call one f of x, and let's call the other g of x. So we can make, if you want, new ones. Well, what do I mean by that? Well, we could add or subtract them together to get a new one. We can multiply them together to get a new one. Or we could take one and divide it by the other one to get a new one. And then the very last one that we deemed is this composition, and that is where you don't multiply them per se, but you plug one into the other. So we're gonna dig into this in a second. But we need to write this down. Again, this is a topic that you would have learned in a college algebra course or a pre-calculus course. That if I give you two expressions, which I can call functions, then you can add them, you can subtract them, you can multiply them, you can divide them, and you can compose them. So let's dig a little deeper into this. So here's a great example of how I want you to think about composition. This is a topic that's very important in this class. It's going to be used a bunch, and it's also a topic that is challenging for students. For some reason, we struggle with it. I did when I was at this level. You will at your level. We just struggle with it. It's conceptually difficult. So here's what I want to do. I'm going to start with a function, and I want to play a silly game. So let's just start with the basic function f of x equals 3x squared plus 2. So let's build our level of sophistication. So let's start with a number. Let's say, okay, let's plug in 3. When I plug in 3, I get 3 times 3 squared plus 2. Now, because all these are numbers, I can actually compute what this is. I can compute this. This is 3 times 9 plus 2. So if we do the math, this becomes 29. 3 times 9 is 27 plus 2 is 29. All right, so now what I want to do is I want to be a little different here. I don't want to plug in necessarily a number, but what if I decided I wanted to plug in a letter? So what if I plugged in K? Well, what does that mean? Well, that just means I take 3 times K squared plus 2. Now, I have not told you what K is. All I said is plug this symbol in that is the letter K. And since that's all I've done, then the best you can do is this. You can write 3 times k squared plus 2. You can't go any further. Okay, well, what if instead of that, I said, okay, let's do a different thing of that similar ilk. Let's say I wanted to plug in 5h. So now if I think about the 2 previous pieces of this example, what I notice is when I'm evaluating functions, I am literally just taking one symbol and replacing it with another symbol. Maybe it's a number, maybe it's a letter. Here, I'm going to replace everywhere I see an x, I'm going to replace it with this 5h. So just to emphasize that, I'm going to put this in yellow here. So everywhere I see an x, that is where I'm putting in whatever is inside my parentheses. And so now, if I remember my basic rules of arithmetic, this becomes 3 times 25h squared plus 2, which we could clean it up a little bit, writing it as 75h squared plus 2. Does anybody have a question about this? So this being able to do this will be important in this class. That is, and let me reiterate this, you need to be able to take a function and interpret what happens when you not only put a number into the function, but you can evaluate it at an expression. We call this composition. Okay, so let's go a step further. And again, if you have a question, please don't hesitate to ask. Be it you can chat, you can yell, whatever you want to do, I don't care. What happens now if we up the difficulty level, and instead of putting something like 5h in, what if I said, okay, let's do 3 plus t? So what is this going to mean for us? Well, the function we started with was 3, and then it's input squared plus 2. So what's my input? My input is 3 plus t. So I'll write that in yellow just to emphasize what's happening here. Okay, so when I plug this expression in, when I compose f with this new expression 3 plus t, this function, if you will, I could leave it like this if I wanted, but I could also multiply it out if I wanted. So on one hand, the expression f evaluated at 3 plus t can be written like this, but if we wanted, we can multiply it out. So what do we mean? Well, for those of us who have not done algebra in a while, this thing becomes this. And then we have to do some algebra. So again, this might be like in the back of some of your minds, you might have to get in a time machine and go back to when you learned this, but one way to multiply this out is you do, I think you guys call it the FOIL method in school. But this becomes 9 plus 3t plus 3t plus t squared. I'm distributing. That's how you multiply algebraic expressions. You must distribute. And then you can clean this up inside. This is 9 plus 6t plus t squared. And then I can distribute this 3 to get 3 times 9 is 27 plus 18t plus 3t squared plus 2. And then finally, we've expressed it as 29 plus 18t plus 3t squared. Now, many of you would be quite capable of doing this in a line or two. Some of you need all these lines that I wrote out. Again, let me emphasize, every one of you has a different level of experience with algebraic equations and with functions. So every one of you is going to take a different amount of time for you to understand this page of symbolic, I don't want to say gibberish, but symbolic logic, if you will. Does anybody have a question about this? So it might even be helpful if I put some arrows in to illustrate what I'm doing. Like, what am I doing here? I'm taking this times this, and then this times this, and then this times this, this sort of what we call the FOIL method. And then here I'm doing this, etc. I guess I didn't do it there. I sort of lied. I did it at the next step. So how did I get this line? This times this and this. So look, this is something that some of us aren't going to want to hear, but it needs to be said. One of the things that makes learning a subject like math unique is that everything you're learning is dependent on what you've learned previously. It's one of the unique subjects where you almost have to remember how to do things in previous courses. It just all builds. It's very different than other subjects. Like in history, I mean, you don't have to know anything about the world in 1630 to be able to understand what happened in 1800. In biology, you can study different types of animals and stuff, and they're not necessarily, it helps, but it doesn't depend directly on what you learned in other classes. In calculus, you aren't going to get anywhere if you can't do algebra. You're not going to get anywhere if you don't know basic geometry and you don't understand the properties of numbers and number sense and arithmetic. So all these things that show up in this particular page right here, these are things that you need to become sort of familiar with again, and you can't let it overwhelm you, or it's going to be really hard to learn calculus. And I guess we can argue you could learn the ideas of calculus without being good at algebra, but you can't use calculus because the calculations are going to require familiarity with algebraic reasoning. Does anybody have a question about this example? And I don't mean to beat the dead horse, but with this. So if if you think that I'm doing too many steps, well, I'm sorry. And if you don't think I'm doing enough, well, I don't think I could do any more here. I did them all.
Can you do an example like number 2D?
Yeah, so that's where we're going next. So these guys are extremely important. So these guys have a name. They're called difference quotients. All right. So an important expression in calculus is called the difference quotient. So what is a difference quotient? So it's exactly what you see in 2D, only it doesn't have to be with the number 1, and it doesn't have to be the letter H. So what is a difference quotient? This is something of the form. Now, don't be afraid when you see this. I'm going to write an A here and an H, and then I'm going to write. So why are we calling this a difference quotient? It's called a difference quotient because we have a difference in the numerator and we have a quotient in the sense that we're dividing by it. So here's what's important to understand is the following. A and H can be any numbers, but we know obviously H can't be 0. Right? You can't divide by 0. Now, we're going to see soon enough, most likely on Tuesday, why this thing is important. Where does it come from? But if, you know, one of the things I like to do when I'm teaching is I'd like to give you guys context for why things are important. One of the downsides of many, I guess, math classes is that oftentimes we're asked to do things and there just doesn't seem to be any rhyme or reason why we're doing it. And that's unfortunate because all of this stuff that we're asking you to learn is motivated out of human necessity to understand the world around us. So there's motivation for all this stuff. What I like to do is try to remind you of that every chance I can so that we don't just bore you and bog you down with endless calculations. I guess I should have written this better. An important expression in calculus, not an important expression calculus. So to see where this comes from, let's draw a picture. Well, let's take a function. Let's take the squaring function. That's a nice function. So just like in the problem you see, problem 2, I'm going to take a function. I'm not going to use 3x squared, but you can see similarities with that problem in mind. I'll just do x squared, and I'm going to set a equal to 1. So that means the different quotient looks like this. Now, I could write out what this means, and I will in a second, but I don't want to write it out yet. So before sort of evaluating, let's look at the geometry or the geometric meaning. So when I say geometric meaning, this is when I want to combine geometry with algebra. And the geometric meaning is, you know, if you look at the official title of this course, it's called Analytic Geometry. And that's just fancy words for something you learned in an algebra class, that you can visualize equations and functions by looking at their graphs. So if we go to the next page, let's draw a graph. So I'm going to draw my XY axis. And what I'm going to do is I'm going to sketch a piece of the function y equals x squared. So what does the graph of this look like? You guys will remember it's a parabola, so it's graph sort of. I guess I should be a little more careful. That's sort of bad. So it looks something like this. So this is not to scale, but that's okay. So let's remember a few points that are on. Actually, you know what? Here, let me be more careful so I don't lose you all. Let's label some things and we'll sketch this the old-fashioned way. So maybe this is 1 and then this would be 2, right? And so what's the graph look like? Well, the graph would be, so the graph's going to come up at 1, it goes through this point, and then at 2, it goes through 4. So get my blue out. So the graph's going to look like this. Something like this. Not perfect, but you can go to a calculator and figure it out. So let h be approximately 0. Doesn't have to be 0, but let it be and let's just assume that it's bigger than 1. Okay, so if I do that, if I assume that h is a little bigger than 0, then that means that this point right here, for example, what is this number? This could be 1 plus h. So for example, this is the point. What is the coordinates of this point? This is 1 plus h, comma, f evaluated at 1 plus h. So I know that looks scary, but that's what the coordinates are. And what is this point? Well, this point right here is the point 1 comma f evaluated at 1. Now, if I go and draw a line between these 2 points, I'll call it red. So here's the key observation, and this is why this is important. So note, the slope of the red line is, you'll remember the equation of a slope. It's this difference in the y value, so it's f over evaluated at 1 plus h minus f evaluated at 1 all over 1 plus h minus 1. And so if you cancel out the 1 and the minus 1 add up to 0, you'll get the difference quotient. So if I recognize that this and this add up to 0, then I am left with this expression. So what I want you to understand now, the key or it's not the key observation, but the key point, the key idea here is that this scary difference quotient that I introduced in problem 2D, and we're going to see many times moving forward, it is going to be important for us in calculus. And the reason that it is important is because it has this very important sort of geometric flavor, and that is, it is the slope of the line going through 2 points. Does anybody have a question about this? So you might say, okay, so why do we care about this line? Well, remember what we talked about on Tuesday when we tried to motivate calculus. When we were motivating calculus, I asked you 2 questions. I asked you, what is area? And then I asked you, what is velocity? What is speed? And then I talked about how really velocity and speed are just this special case of a more general idea, which is change. So this difference quotient what it will do is it will provide us a method for measuring change. What change? That's a great question. What change? What do you mean measuring change? Well, when input changes, how does the output change? So, in terms of symbols, when x changes or varies, what happens to f of x? Now, you still might be confused by what all this means, but I encourage you to look at the graph of x squared. You will notice that it doesn't have the same steepness at any given point. In fact, the larger x gets, the steeper it gets. Let me illustrate this by switching the page for you. I want to show you something. So one of the websites that I use all the time, and I have it on my phone, and it's free, is this thing called Desmos. So if you're not familiar with it, I would highly encourage that you check it out. So hopefully right now you guys are seeing Desmos, hopefully. And so what I want to do is I want to graph something. I'm going to graph f of x equals x squared. That's what I had on that page. So I'm going to move this around a little bit. What you'll notice is that this curve does not have the same steepness everywhere. If I zoom in on it, you would argue it's flatter here. Hopefully you can see my mouse moving. It's completely flat at 0, and then as I move along it, it becomes steeper and steeper. A better way to think about this, excuse me, is if you were walking along this curve, you would say, okay, I'm going down the hill here. Now it's relatively flat. Now I'm going up the hill, but it's getting steeper and steeper and steeper. And we want to be able to quantify this steepness. To illustrate what I mean even more by steepness, what if I change the function a little bit? Let's call this guy g of x, and let's say it's 3x squared. Well, if I asked you which path would you imagine this is, you're walking from left to right. If I imagine this dot as you walking, I'm going downhill, 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 but it's not as steep anymore. Now it's flattening out, flattening out, flattening out. Now I'm completely flat. Now I'm walking uphill, and it's getting steeper and steeper and steeper. So what we'd like to do is quantify this. And here's our idea on how to quantify it. And this goes back to sort of how some very smart people like Newton figured out how to define change, and hence things like speed and velocity. If we look at a specific line, so let's take the point that we were talking about before. Let's say 1 comma f of 1. We'll label that, and let's go over here and look. And then let's pick some value h, and excuse me, let's take 1 plus h, comma f evaluated at 1 plus h. And we're going to let h vary. Maybe starts at so there's my h. And so if you look back at the slide, you'll say, okay, I see something, what's happening here. So now I want to draw the line that goes through those 2 points. So you might not be able to do this in your head the way I'm doing it, but how do we do this? Well, the line is given by y equals mx plus b. You have these slopes. So we know that it goes through one point. It goes through the point y minus. Well, let's calculate that slope, by the way. Let's just calculate it. So we need something which I'm going to call m. And what's m going to be? It's going to be this difference quotient, f evaluated at 1 plus h. And then it's going to be minus f of 1. And what I'm going to do is draw my line. So it's y minus 1 equals m times x minus 1. And so what you'll see is that as h moves, that line, that blue line, is the line that the difference quotient has as its slope. Let me hide this. So I'm going to change the scale a little bit so that you can see a little more of what's happening. Okay, so what's the important observation? Well, the important observation is as follows. Watch what happens to this blue line as h approaches 0. When h gets close to 0, that blue line looks more and more like it's doing what? Well, it looks like the blue line is not touching the red line twice. Like right here, we would argue, okay, the red and the blue lines are touching twice. Or excuse me, the blue line intersects the red curve twice. But as h gets close to 0, what we start to notice is that blue line begins to look more and more, and the word you might remember from your days in geometry class is tangent to, if I zoom out, you'll say, oh, okay, it looks like it's just touching it once. Touching twice. Now, you might say, okay, well, what good is that? Who cares? What are you getting at? Well, let me change some numbers around. I'm going to modify, and don't worry about stressing out how I'm getting this. take some time to learn how to do this. It's not terribly difficult, but I'm trying. I want you to just pay attention to the picture. I don't want you to pay attention to what I'm typing in right now. Okay, now what I'm going to do is I'm going to move the point in a different way. Look at this blue line now and think about what you know from your days in algebra. I think we'd all argue that this is a steeper line than this, the blue. Think blue. Not so steep, steep. Not so steep, not so steep. Heck, right around here, it's flat here. It's horizontal. It's slope 0. Here, steeper, 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 steeper. Think about what you learned in algebra about the slope of a line. What did the slope of a line do? It quantified how steep our line was. Okay, so what we're trying to do here, why this difference quotient is important, is what it's going to allow us to do is it's going to allow us to say, okay, great. That line is not so steep as that line is. This line has negative slope. This line has positive slope. This line has negative slope, and it's also, quote unquote, steeper than this guy. So one of the genius ideas that calculus is based off of is that we can use this idea of the tangent line, and I want you to think of this as a tangent line. If I zoom out, it'll be a little easier to convince yourself. I want you to think of this blue line and its slope as a way of quantifying how steep the red curve is at any given point. How steep is the red curve? Well, we're going to use the slope of this blue line to tell us that, or not to tell us, to define it. And then we'll be able to do all other types of interesting sort of calculations and ways of quantifying things. So, but before I leave this screen, and again, don't get overwhelmed. I'm not going to test you on this screen or anything right now. I'm trying to motivate an idea. Does anybody have a question about this picture? And by the way, it's not difficult to learn how to graph on here. It's very self-explanatory. Okay, so the point of this picture is that the difference quotient is the key thing to understanding the slope of this blue line. So the difference quotient is the key to understanding this blue line. And this blue line is key to quantifying how steep the curve is. Now, why do we care about how steep the curve is? Well, the steepness of the curve is exactly measuring the change in the function. So visualizing change comes down to looking how steep the curve is. So believe it or not, even though it seems completely ridiculous right now, this blue line is going to be the key to defining things like velocity. It's going to be the key to defining speed. And believe it or not, at the end of the semester, you're going to see this blue line is actually a key part of understanding area under a curve. So the blue line here is extremely important. And the geometry doesn't seem that bad, but the bad news is that that blue line comes down to studying these difference quotients. And as you know, that these difference quotients are difficult to play around with. So this seems like a sort of good place to end, but I think what we should do before we end is I think we should do one of these examples. So before I do that, does anybody have a question or a comment that they want to make? All right. So what we should do is we should just do one of these, and we'll go from there. So I don't want to do the one that's on the homework because that'll steal the fun from you. So let's move like this. So to analyze the quotients, we work as follows. So let's do the one we had. Let's remind ourselves that f of x was x squared. And what I like to do is I like to think of these things as puzzles. And you got to do each piece at a time. So what do we have? We have f of 1 plus h minus f of 1 over h. So right now I think of this as a puzzle that has 3 pieces. And so I have to get them all situated. The first piece is 1 plus h quantity squared. The second piece is 1 squared. And then the third piece is just this h. So it will be helpful if I annotate this. This piece right here is just f evaluated at 1. This piece here is f evaluated at 1 plus h. Okay, now we have to do some algebra. We have to multiply this out. This becomes 1 plus 2h plus h squared. This becomes just 1, and then this is all over h. Now, a pretty fascinating thing happens. When you do it this way, everything that doesn't have an h will add up to 0. What you'll notice is that I have a positive 1 here, and that cancels with this negative 1. And so I am left with 2h plus h squared. And the way I like to handle this is I like to write this as 2h over h plus h squared over h. And then once again, I have some things that cancel out. H over h is 1, and then this cancels with this. And at the end of the day, that scary looking creature was nothing more than 2 plus h. Now, most mortal human beings are going to have to spend more than that minute that I just did on this. If you want to learn this, if you want to learn and be able to do this, it is going to take time for you to understand this example. Do not get overwhelmed. Do not get stressed. Do not think you're stupid. Nobody's stupid. This is difficult to learn. It will require multiple attempts. Does anybody have a question about this while we're at it right now? If you're unsure about how I reasoned anything, please let me know. Now, if I can just point one thing out, notice this expression has a 2 in it, 2 plus h. If I were to go back to Desmos and look at a particular thing here, if you look at the screen, don't look at the picture right now. Well, you can look at the picture. If I come over here, see where it says m equals 2.01? This m is the slope of this blue line right here. So if I decide to make h small, what you'll notice is the smaller I make h, the closer this number m gets to 2. And that is not a coincidence. We're going to see that this pattern is exactly what makes everything we do work. But what I want to illustrate to you is that when I put this blue line, when I try to draw the tangent line to the red curve at this point 1, 1, the slope appears to be 2. And that is not going to be a coincidence. It's going to be based off of this calculation. When h is small, what is 2 plus h? It's close to 2. And so if you study what I've just talked about, and I'm not saying it's easy, but if you take the time to think about these examples, what you'll notice is there is a connection with this symbolic algebra and the picture. So I'll leave you with that. If you guys have any questions, I encourage you to ask. If you do not have questions, then I'd say Godspeed. I will upload all this, and we will talk more about homework 1 on Tuesday. All right? Anybody have questions, comments?
So you're going to extend the due date of the homework?
Oh, yeah. I got to fix that anyhow. I don't know why. And look, I mentioned this last class. I prefer, look, it's easier for me to keep everything lined up if you guys turn things in on time. But I will never take off points if you turn something in a couple days after I put a due date. But I will fix the due date for this. So don't stress about that. All right? And we'll talk more about these problems on Tuesday. But again, the best learning happens is if you actually try all these problems. And then once you see someone else do them, you understand how they work. That's the best learning environment. So don't just wait till Tuesday to have us do them together. Try them on your own. And then ask questions. Shoot me an email and ask me about problem 4 or whatever. You know, I'd be happy to help. All right? All right, well, listen, if I don't hear, I'm going to stop recording, and then I will wait a few seconds. If anybody sticks around for a question, that's cool. Otherwise, have a great weekend and be safe. Take care.